And today he'll be talking to us about patterns and oscillations in counterdiffusional systems. Thanks.
Thanks. And thanks for coming and having me at Nimbus. It's great to be here. For some years, I've been working with Steve Thompson, who's a chemist. Tim Lincicchi was a master's student who did some experiments, and then Bahauddin is a PhD student in mathematics who was then working to model some of the fun and interesting experiments that Steve has going on in his lab. And what I'd like to do is so it's going to be more of a math chemistry talk, but there's certainly, I think, implications for biology that I'd like to think about, and if anybody wants to think about it and have ideas about it. These experiments are to a large extent aimed at understanding this is a structure of ammonium chloride, which is, if it's out as particles in the atmosphere, as an aerosol, so a nanoparticle. And Steve wants to understand the chemical processes behind aerosol formation. But he's also been involved in the STEM education. He ran a STEM education center before he retired. So a lot of these experiments were things that he was doing at all levels: elementary school, middle school, high school, undergraduate courses, graduate courses, because they're complicated, but they're fun. And I'll show you what that means, but then I'd like to focus on the simplest one of them, one that's almost boring mathematically. But what I'd like to show is, and really that's maybe the point of the talk, is that with some things that Chapel here is learning in PDE course, you can figure out some things that chemists have been wanting to know for a long time about these reactions, these very fast, complicated reactions. And I'll show you why they can be complicated. And then we'll probably stop there, but I might go on and show some more of the mathematics and things you can do to really look at the oscillations. But let's just look at one of the basic setups. We're looking at producing aerosols, and what you see here is a chamber which is about this high in reality. And at the top is a drop of hydrochloric acid. So this is just a little drop, like a standard old half centimeter across drop. At the bottom is a drop of ammonia. Ammonia is a base. So these are liquid solutions, but they sublimate. They give off, or sublimate is not the right word, but they give off vapor ammonia here, and vapor hydrochloric acid from the top. Ammonia is heavier than air. It's going to actually opposite. This is somewhat done the wrong way. So I want you to think of it as there's diffusing into each other and then reacting. Now what's happened here is that we have a much stronger solution of ammonia than HCl. So the reaction is actually occurring. If we look, here's a close-up of the drop at the top, the HCl drop, and the reaction is occurring right there off the HCl drop at the top. And we'll look at some video of what's happening there, but as it falls down, there's some fluid dynamics. It's interesting because the crystal fall is curved for some reason. I'm not going to give all the explanations now, but we'll just look at these, and then I'll focus on one set of explanations, and then we can start playing around with this more if we like. And if you look from the top, you'll see this. What you see is that basically what happens as time goes by, the concentrations of ammonia and HCl are changing. So the position of that reaction zone where the ammonia and HCl vapors are interacting and eventually forming the solid precipitate, the white powder that you see, that reaction zone is moving out with time, and you're forming these. It's interesting because it's not uniform. It's some band pattern that's forming as you move out from the drop there. So that's one thing we'd like to understand, that band pattern. By the way, ask questions as you go along. Feel free to ask questions at any time and clarify things, because there's a lot going on here, which I won't note everything about it. But that's a little schematic. Blue means base in this talk. Red means acid, and here we're forming that crystal fall that's coming down there. All right, so here's a video that I did of what's happening at one example of this drop. So again, this is just a video, a close-up of the HCl drop at the top. And this really is a drop. It's like half a like a small drop, a half centimeter across. And it pulsing for some reason, which we should think about. It's not really uniform. There's a more strong flow down of that powder down in the middle. The powder, by the way, the white powder is ammonium chloride. It's made up of a lot of small particles. The particle size distribution is something we'll eventually be interested in. It was Newton's favorite chemical because he used it to visualize, in some ways that we want to do here, to visualize turbulence in air and visualize how things, to be able to see fluid flow. The nature of what's happening at that drop is dependent on the concentrations, the temperature, lots of things. Here's just another example, not quite as fun because it wasn't pulsing the same way. But if you look at that, I never really have gotten a video to show exactly what I want here, but you might see a little bit of we call these micro tornadoes because, and sometimes you've seen, I don't have a good video yet, but you can see that rotating of that flow there. And we claim actually that although tornado formation is not totally well understood yet, that a lot of these nucleation and growth processes that we're talking about here could play a role in tornado formation, not with ammonium and chloride, but with water vapor that's condensing and changing a phase. You can do this in a lot of different ways, and this helps just to see why, and to probe what's happening, what might be involved. In this case, we have not a beaker, but like a little container of ammonia here and HCl there. So in this case, something's forming off of the ammonia source. I call this a microgeyser, although it's not really the right mechanism, but this is how we formed that structure. Looks kind of like a catenoid. I'm not sure if it is, but that's just for fun. I'm showing this mostly because I'm going to show another picture from a paper back in the early 1900s in a little bit here, which looks almost like that some group in biology was interested in looking at plant pattern formation. Here's something interesting, because here what we did was the following. So I want to just pause this for a minute if I can. Well, let's just watch it. In this case, what we have at the top is a drop of sulfuric acid. So it's not hydrochloric acid in this case. And there is a drop of ammonia, but it's not right under this acid drop. It's somewhere off to the side. Because in this case, what I want to see is, besides that crystal fall, those small particles that are coming down, right in the midst of them, you get this crystal that forms, that goes up, and when it hits the top, it starts forming these dendrites. And if you let it go on more and more, you see what's in the next slide. That's just a long-term picture of that same experiment in the dendritic. It looks almost like lightning. I call it solid lightning. And for more reasons than it just has that, not sure if it really has the structure of lightning, but so you can do this. Here's just a bunch of them, a bunch of drops of sulfuric acid at the top. There's a drop of ammonia somewhere, and it's fun to have students think about why the width of this crystal fall changes depending on the relationship of the drops of acid and base. But here's something that when you do an experiment like this, you want to, normally we have Petri dishes sitting around in the lab, and we do this in Petri dishes, but I want to be able to get like a flat side here so you can actually get a nice, we have a nice microscope that's built to look from the side. And to do that, I was using different things. So instead of polystyrene Petri dishes, a glass box. And it's interesting because, well, you saw a little bit of that crystal structure forming here, but it doesn't get very big. In fact, it never gets very big when I do it in this type of a box. We've changed the material of the box. And here is an example where, in order to get the right height, I was just putting a bunch of glass microscope slides at the bottom of the box here, and he never formed that crystal, that micro-lightning solid crystal that moved up. So that was interesting. It seems to be telling us something, about something that's happening here that's important for the reaction. And so you can play around with these things, and you don't have to know a lot of, or understand a lot of the chemistry yet to start just playing with some things in the classroom, things about the relative diffusion rates when you're putting drops various different rate distances from each other. In fact, that's something that I want to look at. Convection comes in here, mass transfer, energy, or mass conservation, energy transfer, lots of ideas that you can just start experimenting with. And the beauty of this, and Steve's goal of this originally, why he originally got into this, was not really to understand the aerosols, but was able to do in a chemistry classroom almost what we do in a mathematics classroom. In other words, in a chemistry laboratory, normally what you do is you have a big beaker, another big beaker, and you pour this one to that, and you place a bunch of waste, and then you go through your chemistry experiment in the lab, and then you get 3 numbers, and you hope that they're whatever, that kind of thing. But so and I'm not complaining about that. I'm just saying that Steve's goal was to be able to do what's so fun about math, and maybe one of the things that I liked about math is you have a piece of paper, you do something, you scratch it out, you do something else, and you can experiment a lot. There's a lot more freedom because you're not tied to the real world. I mean, you can just play with things. But so Steve's goal here was to make, and this is just one example, but in this example is that even though hydrochloric acid and ammonia are, you can get weak enough solutions so that it's something you can bring even to an elementary school. But the goal is to be able to put down a drop. You have a little squeegee thing. You put down a drop. If it doesn't work here, you take a Q-tip, you erase it, you put another drop somewhere else. You play with it, and you can start doing, and I loved it because you can learn a lot just not being told right away what's happening. You can get some feel for all these experiments or these processes. But they're complicated chemically. And this is some idea of what's going on chemically that we've synthesized from the literature. People don't really know, by the way, what's that whole set of chemical mechanisms that involved in taking vapor phase ammonia, gas, G here means gas, ammonia gas, HCl gas, which eventually I want to take all of these. So we just saw these, we didn't see it even coming off the drop, but eventually what we see is some solid phase particles, which are it's a conglomeration of many ammonium chloride monomers. Yeah? Like millions of them before you can actually see this white particle sitting there, many millions of these monomers. So really what you have happening is some complicated system where you're first forming conglomerates that are still vapor phase until, in classical nucleation theory, the way you think of it is that you get a high enough concentration of this vapor phase ammonium chloride. Once it gets supersaturated past some sort of nucleation threshold, it can conglomerate on itself and form through homogeneous nucleation, ammonium chloride solid, which is what we see, which is what we observe. So there's a lot of stuff going on before what we actually observe, the white powder, which is this thing here. And we could go through and model a lot of this, but what I want to do is just simplify it about a simplified mechanism, which just says that we have a vapor phase acid, a vapor phase base, which are going to react to form this nucleated gas phase, in our case ammonium chloride, I call that M, for monomer. Maybe it's not always a monomer, maybe a dimer or trimer. But at some point, when the concentration of that monomer, that's the little M here, gets to a certain supersaturation, a critical concentration M sub C, it's going to start forming, it's going to turn into that precipitate. So you can almost see here why you saw those. Remember those bands that we saw earlier? So we can start understanding, at least in the context of classical nucleation theory, why we might have seen something like this. Because to form this white powder, in this case, it's a little more complicated. We're not just, I sort of took a very simplified version of everything that's happening here. We just have a high supersaturation of the ammonium chloride monomer until it can nucleate on itself to form the ammonium chloride. In this case, we have a wall here. We have the top of the Petri dish here, and it can actually nucleate on the Petri dish. So we have sort of a wall nucleation. So there's a lot of things that can happen. In fact, it's kind of fun. If you do this on a day that there's a forest fire in Fort Collins, it just bang, the whole thing just, you get powder everywhere because the thing's nucleating. It's heterogeneous nucleation. You're nucleating on those particles there. So it's fun. You can start really understanding, seeing a lot of processes here, just very simply, and So by the way, the reason I went all the way back here is that if you think about that front, this region here where the ammonia is, you have ammonia coming from this side, HCl coming from this side, they meet here. It's a very fast reaction, by the way. And so they're not going to really penetrate much into each other before reacting. That's the way to think of it for now. But as the concentrations change, we're going to be thinking about this, and this will be our main problem. The front, that place where they're reacting is going to move. And as it moves, in this case, think of it moving away from this HCl drop at the top, that the concentration of that monomer that it's forming is going to go up and down. Up while because it's being produced by the reaction, but down whenever it reaches the supersaturation threshold. And when it reaches that supersaturation threshold, well, it goes into ammonium chloride powder, and then the concentration of monomer falls down. It has to rebuild up till the reaches supersaturation, and then so you can see that oscillation coming from this idea of there being a supersaturation threshold. So I'll say a little bit about this later, but the main focus of the talk is really before that. What I want to understand is all the steps, or something about the steps up to that point. So the thing I say, we start the reaction, or we start the experiment, I just put down some ammonia drop, and HCl drop. Now ammonia vapor starts to come off the ammonia drop, HCl vapor starts to come off the HCl drop. They hit at some point, eventually somewhere that monomer concentration gets high enough until it reaches supersaturation, and then boom, you see some powder forming there, and that's where I want to stop for now. I just want to think about the processes up to that point, and then we can go on and understand things before that. What that means is that there's sort of two parameters if you look at a very simplified version of this, which is the rate of the reaction rate constant for ammonia plus HCl forming that monomer, and then that supersaturation threshold. How much monomer do you need before you're going to form the white powder, the precipitate? And these things are things you can't just look up. It's hard to measure that. It's a fast reaction. Okay, you can look up that because someone in the 1950s did a following experiment. It's quite complicated, and what you do is you get a big chamber. You try to push in a bunch of ammonia and a bunch of HCl at the same time and have it very rapidly mixed, and then you hope that it all reacts with each other, and you sort of do that until you get the right amount to nucleate, and then you sort of try to figure out that nucleation threshold. So there actually is a number in the literature from the 1950s, which hasn't been repeated or tried to be improved upon since, that we can compare what we want to get out here. What I want to do is for someone from like a PDE class, maybe just a little bit more, you're going to know the diffusion equation, maybe a little bit about law of mass action, because you have to know how to, a little bit how to model a reaction. You put that together. Can we do some simple experiments with Q-tips and a little bit more complicated than that, and try to figure out those types of things? And that to me is going to show some power about the mathematics by really understanding the diffusion equation. But there's also a lot of history behind this, and that's what I'd like to show you. But the preview is this. Again, I'm only going to be interested for most of this talk, maybe all of this talk, in all of the process, this reaction up to the point where you first see the powder. So it's going to be way before any of the complicated experiments that we saw. And we're going to be working classically. This experiment that I'm going to be talking about, maybe it's a little bit premature. Yeah, it's a little bit premature, but not too much. So this black curve here, forget about the purple ones. We're going to be understanding this graph for most of the goal of the talk is to understand this graph. And over time, at some point in an experiment, think of this as where the HCl drop is or where the ammonia drop is. Ammonia is coming this way, HCl is coming this way. They happen to meet here in this case, and they're forming the monomer. So this black curve is the M, it's that monomer. As time goes on, you get more and more monomer, so here's a later time. Here's a later time. You notice that the peak of that monomer is moving a little bit to the left, in this case, towards the HCl, and eventually monomer gets high enough at some point in time and space so that it reaches this green line, which is the supersaturation threshold. Bang, right here, you're going to get the white powder. Okay, so that's what I want to understand, and I want to understand as we change the concentrations of ammonia and HCl, what happens, and see if we can learn something about this reaction in that way. But what we call this, because there's a lot of ways you can probe this system. You can put the green, the blue as ammonia, the red is a base or acid or some other acid and base, and the green is the white powder. And as you put these in different, what we call topochemical, you can do different topochemical experiments to probe different ways of exposing them to each other and see what happens. You can put dry ice in there and see what happens when you drive it in some certain way, put some gradient on. So there's a lot you can play with and learn and do environmental studies almost, build a little microenvironmental chamber by doing these topochemical experiments. But what I want to focus on the top is the most boring of these, almost the most boring, except it kind of stumped me for a while to look at Steve's data and to figure out the right thing or what exactly was the right thing to say about it. So I think it's fun. And it's just this one, where we have a tube, and there's HCl on one side, ammonia on the other side. We let them both come in, and we look at where the white powder first forms. And I want to understand that. Where is it going to form? How long is it going to take? That kind of thing. And what can we learn about this rather complicated reaction by doing that? But before that, just because this is a math bio talk supposed to be, this figure is all from a paper from 1926, Note on Rhythmic Compartmentalization in Plant Membranes. And so this might look at like some of the rhythmic oscillations that we get in the experiments we do, but they certainly thought so back in 1926. This is an experiment very much like the one I showed you with what I call micro geysers. This is actually it might not, I think it is ammonia actually, and you're forming this white powder off of it. So it's very, this is exactly the figure from that. And we are now doing experiments like this in other biological systems, for example, anthocyanins, which are plant pigments, and showing that you can get a lot of these same oscillations and periodic structures in that system. So there's biological ways of going with this. Plus, the experiment that I want to analyze here is one that's done in throughout the country. A lot of first-year chemistry labs do the experiment that I want to explain here. And it's actually at CSU. I know it's done in both the Chem 101 on 101, 113, is like the first lab for introductory chemistry. It's also done in the lab for introductory biology, the following experiment. The one I just explained before, though. What you do is you get a tube like this, and typically it's 120 centimeters long. I'll say why. And you put a cotton ball on one side, another cotton ball on the other side, and on this side there's HCl solution in it, and this side there's ammonia solution in it, and the gases are going to diffuse through the tube until they hit, and at some point your job as a student is to measure where and when, where actually only, and the way it's explained, that cloud of ammonium chloride precipitate forms. So very much like this. White ring of ammonium chloride here. And then you measure the distance to the ammonia, distance to the HCl that white ring first form, and it's not going to be right in the middle, so you have to explain why, and from that ratio say something about what happened there. Okay, now this experiment appeared in really the first laboratory textbook, the text or the laboratory manual that set the stage for doing laboratory experiments in the US at least. For the next 100 years. Actually, it's the 100-year anniversary of this. William Chapin at Oberlin College in 1918, that was the first edition. And he gave this experiment, and it's a nice experiment. But it was based on a lot of history, which I'd like to go through, because we teach diffusion in like a PDE's course, and normally through the way that Fourier thought of it, to derive the diffusion equation. But I'd like to show what led to Chapin, because it's all tied in with the history of the idea of deriving the diffusion equation. So in that history, I like to start with John Dalton, the Dalton of Law of Partial Pressures, that when you have a mixture of gases, the pressures of each gas, you just sum them up to get the total vapor pressure there. The reason I'm starting there is because he did the following experiment, which actually kind of leads to what we are doing here. But in his case, he had one gas in a container here, another gas in a container here. He had some tube that can go through it. It's almost exactly what we did, right? And so without cotton balls, this is what he was doing back in, whenever I said there, 1801. So, and he was looking at the sort of the rates at which the gases come. Now, they're not reacting with each other in this case. It's not ammonia and HCl, but he's looking at the rates at which one gas goes into the other tube and showing if they're different or not, and trying to understand what's happening there. 1810, this is the first chemistry textbook published in the United States, a grammar of chemistry. This is in Steve's collection, Steve Thompson, the chemist I'm working with. And what's funny is beautiful. But what I'm showing this for is to really set the stage for Fourier's analytical theory of heat, where he wrote down the diffusion equation. But the context here, just for those who haven't thought too much about the history here, is that at the time, it wasn't until maybe early 1900s that really the idea of an atom, although it was there a long time before, people really became really established. Right? Boltzmann in the late 1800s had to fight for that idea. But Fourier down here in 1822 is going to set down the ideas for the diffusion equation. And you're thinking about diffusion for, like, say, heat, which is what, you want an analytical theory of heat. What is heat is the question that, you would naturally start with if you're going to do some mathematical modeling or write down the equations for it. And in this textbook, they're saying, they're talking about the two opinions on caloric heat, kind of. That one is that it's some fluid which pervades the pores of all bodies. And you put it there, and then you put in your hot thing, you put a cold thing, that hot fluid is going to flow into that cold thing. And it's like, really, you wouldn't know. I mean, we should ask ourselves, why do we believe, and why do we not believe in that now? Or what experimental evidence do we have for that we actually know as, say, mathematicians to really understand why we think of diffusion the way we do. And the second is that it consists of the minute vibratory motion of particles, that we have these little particles moving around, and somehow that motion will transfer from one place to another. More like what we actually would say it is today. Okay, so the reason I put that up is because here's Fourier, 1822, analytical theory of heat. I put another red dot here because in 1897, I think, he had first given a version of this which wasn't accepted. And so he published it in this book later on. The only reason I show this now, well, except that it's going to lead to the overall story here, is just the beginning of this. I don't know if you ever read Fourier's Analytical Theory of Heat. It's such an amazing book, not just because the heat equation appears here for the first time, but because dimensional analysis appears here really for the first time. And but he has to do this to understand heat and write down an equation of heat, write down the diffusion, the heat equation, in the context of that two prevailing ideas of what heat was. And so he sets down something here. It says primary causes are unknown to us. We have those two ideas. But are subject to simple and constant laws which may be discovered by observation, the study of them being the object of natural philosophy. Heat, like gravity, penetrates every substance. It's so beautiful, he wrote here. But he's saying, I almost feel like this, now I sort of learned from Fourier. Now when I go into, say, a class, or when a student comes and wants to work on something, and you're like, where do I start? What do I do? I don't know. I'm kind of stuck. I don't know everything here. He's like, you have to start somewhere. You put something down. You look for the general principles. That's what Fourier did, and that's how he got. He didn't know everything about the problem, but he wrote what he could down, and he went on and he did it. Anyway, so you can go on that, but I just thought that's a beautiful book there. And from then on, when Fourier Fourier's way of writing down the heat equation, you basically write down Fourier's law for heat, that the flux is proportional to the gradient of the heat profile. And what's interesting is that for quite a while then on, Ohm, I didn't put Ohm down here, but if you actually read Ohm, he was referring right back to Fourier when he wrote down Ohm's law, which is that the current is proportional to the gradient of some potential. Fick, even, right? So Fick, by the way, wanted to study mathematics, but his brothers told him that there aren't many physiologists doing math, so he'd be able to do a lot of stuff. He went in physiology. That's what he did, and he did exactly what they said. But what's interesting is that what he referred back to, and this is what I want to get to, he was referring back to experiments that one Thomas Graham, that we'll look at next, was publishing on diffusion of salts in water. And what he says is that Graham was just doing these experiments, and it's regrettable that he didn't really write down, the mathematics of it and really think about the quantities here. So that's what Fick endeavored to do. And what's funny looking at Fick is that even though Fick, you sort of talk about Fick's law, which is that for chemicals, quite a different problem really physically, isn't it? That you have these molecules moving around, and he just says that the concentration, that the flux in this problem here of molecules, of diffusion of molecules, is proportional. The flux is proportional to the gradient of the concentration profile. But what he actually wrote down first, if you actually look at, it's kind of neat. He was doing this in a funnel. So he had like salt, I think, and diffusing in a funnel. So he wrote down a sort of a diffusion advection equation, because the Q is the area of the cross-sectional area of the funnel. So Fick's law first appeared in kind of a, and this actually gave me an idea when I looked. He put a negative there too, by the way, which is interesting. It's fine. K just has to be negative, what it is. But so that's nice there. But a lot of people from then on, Maxwell actually went back and criticized Fick because he's saying he wasn't really thinking about what was going on chemically. It was just all an analogy to Fourier and writing down that Fick's law. Then that's what they were doing. All right, but Thomas Graham is going to be essential for us here because it's really going to come back to the experiment that I want to do with the counterdiffusional system. Graham was looking at, actually Graham is the guy who actually decided to call diffusion diffusion. Even though the word diffusion had been around, we saw it in the quote I gave from Dalton. It means like to pour something, so it might not be the greatest name for diffusion, but that's all that says. But Graham went back to the experiments that Dalton did and did various versions of them. This picture I showed earlier for Dalton's experiment was taken from a paper that Graham wrote. So this is Graham's depiction of Dalton's experiment. But one of the things that Graham did was do a Dalton-like experiment, but you'd put one gas on the top chamber, another gas on the bottom chamber. In the middle, he put something like a pot, a clay pot, because it's kind of porous and the gases can get through, or a membrane of some sort. Or in something where there's a non-penetrable membrane, but just one hole. It's called effusion, when you just have one hole and you sort of are looking for a very slow, once in a while, a molecule will get through. I took this simulation from Boltzmann 3D, which is an amazing teaching tool. You can actually watch like Brownian, the motion of molecules. So you can just Google Boltzmann 3D and download this program. But this is a simulation then of Graham's experiment where he had like a small hole relative to the size of the gas molecules, and what he wanted to measure was the rate at which, in this case, one red molecule has gotten through. We'd wait long enough. Once in a while, a molecule will get through this hole, and you'll get some blue ones here, some red ones here, and you want to look at the rate at which that occurs. And see, actually, in this case, we'd observe that, hey, the red molecules are getting through a lot faster. You have two of them. Twice as fast. Oh, okay, but now we have three. Anyway, so it's not many particles through yet, so we have to go on for a while, but that's the experiment that, now it disappears, so. Okay, so Graham himself didn't really set down the law. We saw that Fick didn't observe that as well. But Thomas Starkey Thompson, a little bit later, wrote down the following law, which is now known as Graham's law of effusion. And it just says that the rate at which the gas A gets into the other chamber divided by the rate the gas B gets into the other chamber for it is equal or equal to the square root of the inverse ratio of the molar masses of the gases A and B. And the reason that Thomson gave was that if you're at the same temperature, the kinetic energies are going to be the same, and then you just solve, and that's what you get. Yeah. So that's quite nice. And it fits the data that Graham was getting. Alrighty, so there's a lot of fun history here about who was whose PhD advisor and all this kind of stuff, but so I'll try to cut it short here. Stefan's problem, free boundary problems. One of the things he was really interested in was really understanding diffusion and putting a lot of these experiments together, looking at what Graham did and Fick did, and Loschmidt was another name that we should talk about here. But, Loschmidt was working with Stefan in Vienna. But one thing that Stefan did, which is really going to motivate what we do, is that he was looking at the diffusion of ammonia and HCl in liquids and looking at the rate at which they react with each other. So basically what he did was something like he had some container, and he had ammonia on this side, HCl on this side. He let them gum into each other, and he had like a litmus paper down there. I'm not sure it was paper, but something, and then you could watch the litmus paper change in pH, and then you could tell who had penetrated and who faster, and try to figure out things like that. So that was one of Stefan's fundamental work, setting up free boundary value problems and looking at diffusion. So that is really going, and that's part of the history of why we are working now with ammonium chloride and where Chapin got that idea. Okay, but now I'd like to come back to Chapin, 1918, where he set down the experiment that I want to analyze, even though it's a simple experiment, and see if we can figure out what's happening. This is from a more modern day. This is not Chapin's own text, but this is one of the main texts that's really used, that's sent around, and is a sort of a standard for chemistry, first-year chemistry laboratories. And it's just to do exactly the experiment that we described. You have ammonia and HCl gases eventually reacting for ammonium chloride solid in that tube. And you see here the idea of Graham's law, that what we want to do is look at the square root of the ratio of the molar masses, but since the diffusion coefficient is going to be kind of inversely proportional to the molar mass, then in some sense we're looking at the ratio of diffusion coefficients when we look at this problem. And so what you do is here it says 50 centimeter. Chapin used 120 centimeter. I think most people use 120. What's kind of funny is that, let's see, what does it say here? You take equipment, what you need is, what's funny is he said HCl and ammonia. And normally what you do is you take concentrated ammonia. That's what this means, concentrated HCl. You buy these things from the stockroom, concentrated ammonia, concentrated HCl, and you put those, and that's what it says, to put those into the concentrated ammonia, concentrated HCl. Handle them with great care because they're not good for your skin, that kind of thing. And then you put them in the tube and you watch what happens until you get that first ring of ammonium chloride powder. And then you put the different trials down, average the two trials, and the molecular masses are given to you, and you see if the numbers come out. But the idea is that this distance divided by that distance, of these distances don't mean diffusion coefficients in the little equation I showed before, the distances that we have here. And those distances are supposed to be like the ratio of the diffusion coefficients of the molar masses. So you're supposed to be able to get the numbers. You never get the right number. Yeah. And it's not even, what I want to say, it's not just because of the experiment, it's because there's something we need to understand about this that, in fact, if we understand it, then it's really cool. In fact, we should be teaching here because you'll learn a lot more. You'll learn a lot of things if you do this. So, and so that's what you do. So here really is from Chapin, 1918, William Chapin, Oberlin College. He was talking about, he was doing a lot of really nice experiments in here, but one of them, what's really fun is that he has a description of the experiment, and in the footnote, here's a footnote. He says, to make a sharply defined cloud, you need to use same molecular concentration at each side. So when you get the concentration of ammonia here, concentrated HCl here, they should be of the same concentration. And then he says, commercial concentrated hydrochloric acid and commercial concentrated ammonia are both about 15 molar. So you're going to get the same, pressure. You're going to get the same concentrations. Now, those things are hard to calculate. They're not really the same. And on top of that, what you really want to calculate is the partial pressure of the vapor phase, the gas that's coming off of those solutions. And that's going to be different from the ammonium chloride. In fact, the ratio is not 1. It's equal to something like 4.345. At least that's our estimate of that. Okay. So what's interesting is that, from now on, and you see concentrated ammonia and HCl is what we do in all chemistry, biologically, first-year courses. And there's pinned from this footnote, because Graham, might have been true at that time too, I don't know. He changed it, either number through additions. He eventually took this off, I think. So it's kind of fun. What's even more fun about this experiment is that if you do it, you'll see that first place where the white ring forms, but then that front, that position where the ammonium chloride are interacting with each other, it's going to move down the tube. We should understand why that's the case, but it's going to move from that first position, and it's going to get that same set of oscillations that we saw around that little drop at the top when we did that experiment earlier. And we get these bands, these periodic precipitation bands in the tube, which are really what I eventually want to, which I might be able to say a few things at the end of this talk about, but it's not really my main point. But it's kind of fun because you can do this in all kinds, like a bunch of capillary, you can do this in all kinds of different tube sizes and get a feel for what's happening. Here these are those little melting point tubes. Have you ever done this experiment in the chemistry lab where you pick powder and you put in like a little millimeter width tube and then you stick it into a melting thing and you see how it burns and you I forgot what you learned from that, but it's a melting point. It's about melting point too. Anyway, so we do it in that, and then you can get, so this is a really nice banding pattern because we get what's really classically known as a Lisa-Gang ring. We get rings forming here that are getting wider and wider and further apart. These are what we call Lisa-Gang rings because they were first observed maybe by Friedland and Runge, and later by Lisa-Gang. Lisa-Gang wanted to be an artist, but I guess he didn't have talent as an artist, so he had his father owned one of the first companies to produce photographic equipment, so he started playing around with the chemicals. And what he did was to form something like this. This is a gel. This yellow stuff is a gel. He dropped some silver nitrate in the middle, and as that silver nitrate diffused out, it interacted with some chemical in the gel, and you got those same periodic precipitation banks, which are nowadays mostly known as Lisa-Gang rings. Okie doke. So this would be an experiment that's typically done, that you have the one chemical B in the gel in the tube, you allow chemical A in, and then as it goes in, it periodically precipitates, and you get these Lisa-Gang rings. So a little bit different from what we're doing, because in this case, the whole tube is saturated with chemical B, and we're allowing chemical A in. What I want to do is allow chemical A on one side, allow chemical B on one side, allow them to diffuse into each other, into air in the middle. Okay, well, we're going to do this one too, because why not just do that too with gases? We could allow the whole tube to be filled with, say, ammonia, and allow HCl in, and try this Lisa-Gang type experiment there. We're going to do that later if we probably won't, but I have the slides here if you want to. It's so fun to look at these things, but they're in all kinds of colors. You can do all kinds of Lisa-Gang rings. This is from the cover of the Journal of Chemical Education some time ago. But the point, one thing I want to say about this, though, and one thing that Steve wanted to get onto this as a chemical educator, is that these take a long time to do. It's like months to get these patterns. So you can't just like sit in front of a class or like do some, right? Even that experiment that's done in the chemistry lab there with the one we're analyzing now with ammonia and HCl, it takes a while before you see that first white powder, like half an hour to an hour. So that's like a class period. And so you train, then you have to do it again. And so Steve's real thing, and the reason that we do all these experiments in different sizes, he said, well, can I just do this in a way where a student can just do it, and a couple seconds later, a couple minutes later, you have that white thing, and then you can do it again. You can play with it and do it in a way that's like really in real time, sort of analyzable. And so he began thinking about, okay, if we have a tube this long, this is what the chemistry lab tells us to do. What if we do in a tube that's a little shorter? And then it happens more quickly, of course, but then he noticed that the position changed where that ring was, and then he got confused, and that's where he first really started talking to me about this. All right, so we haven't solved anything yet, but I hope really we're looking at there's some really interesting, we start to really say, okay, we can use these ideas from a PDE course, first year PDE course, to really try to analyze this. All right, so this is what Steve Thompson, my colleague at CSU, has really started doing, is to say, okay, let's really look at this. Here's the tube. We can do it at different lengths. We can shine a laser in and do it in the dark room, because he's thinking maybe I didn't get the same position because it's hard to really see that first ring, and so I'm going to do it really dark and shine a laser in, and I can really see where that first powder forms. And here, just to set down some notation, because we want to solve this problem, what we're going to do, and from now on, HCl is going to be on this side, ammonia is going to be on this side, and we're going to do the experiment. They're both in the diffuse end. We're going to find out where the first powder forms. That's position x sub n is equal to non-dimensional s sub n times the length of the tube. And what we're going to, the typical thing you're asked to do is to look at the distance to ammonia divided by the distance to HCl, and look at and understand that ratio. I didn't point it out, but what you see in the textbook is that this is called Graham's law experiment. This is what Chapin called it when he first proposed this experiment. He said that the distance to ammonia divided by the distance to HCl, is equal to the square root of the ratio of the molar masses. That's the Graham's law statement that we got earlier. Okay. So these days we can actually measure the diffusion coefficient. Oh, and these are related to the diffusion coefficients by basically inverse. So the inverse molar mass is proportional kind of to the to the diffusion coefficient for ammonia. So B here, by little b I mean ammonia, the base, and by A I mean the acid. So this is the thing we should get. So if we can get from the literature the diffusion coefficient for the base and the acid and put these in, these are the numbers that we should get. So I didn't explain this. So S sub n is the actually experimentally observed position of first white powder. S star is what you claim in the textbook you're going to get, that S star is equal to Sn, and that S star is equal to, given by this ratio here. So S star should be 0.455, or if you look at the ratio of distance to ammonia divided by distance HCl, 1.199, larger than 1 because ammonia is the lighter gas. Yeah. Okay. So if you do so that was just why we call this Graham's law, because the number their claim is going to be. Now, of course, if we do exactly what what did we say it was, we should be able to get 0.455. And if we do the concentrated solutions, as Chapin asked us to do, we get 0.41 instead of 0.455. So, I mean, in a long tube, that's a few centimeters off. So that's a significant difference. I should have put like the actual, if you had the same ratio, I have done this experiment. Same concentration of ammonia, vapor pressure of ammonia, and an HCl on each side, but it's not 0.55 either. It's more like 0.43. Again, like a couple centimeters off. I mean, it's significant. You don't get the right number, and we'd like to understand why. And if you understand why, you see a lot of things about the chemistry. In fact, you can see a lot of the things that I've been talking about when I really explain the details of the mechanism. What you're getting, what you observe. Maybe I shouldn't go through this, but what you observe is a whole set of first thing. You set up the experiment. It's hard because you have to put ammonia on this side, HCl on this side if you have a 120 centimeter tube, and you have to do them at the exact same time to set up this experiment. And the ammonia is coming through, the HCl is coming through. About 10 minutes later in this setup, in this setup, or like 26 minutes later, you get this first powder. But if you do it in the dark light, in the dark room with a laser coming through, what you first see is a bunch of little twinkly things. Okay, before the real powder, a bunch of little twinklies. What I claim that is that heterogeneous nucleation, some of that ammonium chloride on the dust particles in there. And then what you see is these twinklies. We call it the parting of the twinklies. In the middle of this twinkly zone, the twinklies part, and there's like a dark space in there. And then in that spark space, suddenly there's a patch of light, a lot of that really fine powder, the real homogeneous nucleation. It's a really fun experiment because it's like getting rid of the heterogeneous nuclei and really being able to do that real homogeneous, that difficult to do homogeneous, really do real homogeneous nucleation, nothing else around. And that's really what you want, that really patch of light. And then even that starts to move, and then you get convection occurring and a lot of fun things. So I'll go through, and there I could show some videos of that's happening. But what I'd like to do then is to understand a number of arguments then. I saved the math for the last minute. A number of arguments for why or why not the. So what I want to claim here is that this number here is not correct, and we know it experimentally it's not correct for the first position of that white powder. But I want to claim that it is the position where you first get monomer. I mean, what I'm saying here, this is kind of a weird statement, but you have HCl coming in, ammonia coming in. Somewhere along that tube, they're first going to form, you're going to get that first particle of monomer. It's going to be somewhat stochastic. You're looking at small numbers of particles when it first forms and so on. But you look on average, what I want to claim on average, that first monomer, which you're not going to observe because it's monomer, it's still gas, is at the position that you're supposed to observe in this chemistry laboratory experiment. But then that position where the monomer is forming is moving. Eventually it gets up to the nucleation threshold, and then you nucleate, and that occurs. Okay? And so you can do a number of experiments to do that. We have you can follow along sort of the more Brownian motion type Einstein experiment if you really just think of random numbers of particles starting, or number of particles starting from one side and other, and they have a sort of an average distance that they're moving each time they bump around, and you look at the average time between bumps, then you can show that. I'm not going to go through this one. I really want to maybe show the PDE model. But you can show where they first hit, then that's going to be at the right position that the Graham's law statement would say it should be. Okay? So, I think that's kind of nice because this is kind of, originally when we were doing this, we were going to kind of be polemical about this. It doesn't work. It's a bad experiment. You're telling people this is Graham's law. We're just nothing to do with little bit to do with Graham's experiment, but it was not Graham's experiment. And I realized, hey, there's something really true about it. You can really say that that number has a truth in it. It's where that first monomer appears. It's just that you don't observe it. So if you were to look at this from a PDE's perspective, you can say, okay, we have the reaction and the diffusion reaction of the acid A, the base B. So here we have they're just diffusing, and then they're reacting, a simple law of mass action type of thing. And until you first form precipitate, these are actually always independent of everything else that's happening. M is the monomer. You're going to form monomer, but this function F here, I showed it earlier. Let's see if I can show it again. But this function F here is 0 until monomer reaches supersaturation threshold. Okay, so you don't get any precipitate. And that's where we're really stopping the analysis for today. So maybe now we understand so you can do some error function type analyses just to approximate where the concentration profile of ammonia and HCl. And the idea is that if you were to look at, say, this is HCl, concentration profiles at various times, the early time, later time, later time, later time, later time, same thing for ammonia, early time, later time, later time, later time, later time. And so at the very beginning, so this would be like an early time. It's hard to see here. You can't really see where but the point is that where they cross is really where that reaction is quickly occurring. And if you were to look at the ratio of blue over red here, it's going to be infinity. But if you look at the ratio of blue over red here, it's going to be 0. Or did I get it the wrong way? Yeah, 0. Infinity here, 0 here, because blue is approximately 0 here. And sorry, if you took the limit as time goes to infinity of the ratio of red over blue here, you're going to get infinity. And here, if you took the limit as time goes to 0 of the ratio of red over blue, you're going to get red over blue, 0. Okay, so that's a calculation that you can do, and you can look also at the ratio of the fluxes of the ammonia and the HCl as time goes to 0 on each side, and use some error function, sort of asymptotic approximations, and you can show that right at that position where Graham's law, so to speak, would say that you should first get the precipitate, there is actually where you first get the monomer. So I think it's actually a very good number, maybe coincidentally, for that first position of monomer. What's cool, though, is maybe this, is that, so you can do a self-similarity argument, too. And you can also look at the following argument. A quite different argument would be to just say, okay, where you first get monomer is going to be where this A times B is the reaction rate to go from A and B into monomer. K times A times B. So this is the reaction term. And the larger K times A times B is, you're going to get a larger rate. So if you were to graph, if HCl concentration profile looks like this, ammonia looks like this, A times B is going to look something like this. And you would kind of guess that where A times B is largest, that's where, so take the limit as t goes to 0 of A times B, and then look at the position where this is max, this critical, this critical point here. It's going to approach, I would think, that position, that S star position, the position where we say the first monomer should appear, because you would think about. Now, that's not true. If you take that limit, doing the same error function approximation and the asymptotics on that, then you get that the position where you first get monomer should be, according to that argument, 1 over 1 plus the ratio of the fusion coefficients, whereas if you look at the same number, we're arguing for Graham's law, I should have the square root here. Okay, so the square root disappears from this argument, which I find kind of weird, but turns out to actually make a lot of sense. Because if you think about the diffusion equation, what's weird about the diffusion equation, especially for, like, maybe not so weird for heat, but it's weird for chemicals because it's not true. I mean, like diffusion equations say you start the experiment, you put some chemical here, and then immediately you have a chemical way over there. And infinity. That's not, but at one point you should say, well, I have to, once this drops below some concentration where it's like 0 molecules, really, you should be dropping it off. And so if you replace this reaction term, A times B, with A times B minus some sort of threshold before you're really going to say reacts, and you do the simulations there, actually you get again that correct thing, the same thing that all the other arguments would have said occur. So I found that kind of nice because it's another sort of new point about the diffusion equation. But I'm going to end, so I didn't really get to so the picture here would be following this. Depending on the ratio of ammonia and HCl on the boundaries here, we're going to get, and these black curves are if we have concentrated ammonia and concentrated HCl, the ratio of vapor pressures at the ends is about 4. And you're going to get a curve from monomer that's going to be moving and moving, where the height, where the maximum position is going to be moving to the left towards HCl until it hits supersaturation threshold, and that's where you're going to first see the white powder. If you use a different concentration ratio, though, it's going to move in a different direction, and you're going to see the white powder occurring somewhere else. What that gives us doing is to vary this ratio, and seeing where all these numbers, where those first white powders appear, compared to the model. So this is the PDE model, actually a stochastic, like a Brownian motion type model, an experimental model, I forgot which color is which. But the point is that in order to get them all to match at the difference, so what's here is the concentration ratio, ammonia at the one end versus HCl at the other end. That's this axis. This axis is where the first white powder appears. And in order to get these 3 ways of doing the analysis to match, or the two mathematical ways to match the experiment, you need to be able to get that right reaction rate constant for ammonia plus base to form HCl, and that right supersaturation threshold. And the point is that we can get numbers that way. That's really fun. This is something you can do with kids, first-year kids in the lab, and you can get the same number that in 1950s was determined for the supersaturation threshold using this big, huge apparatus. And you can get a value for that reaction rate constant, which is not in the literature, but you can figure out what it should be. It's like 0.1 whatever units, so it doesn't mean anything to you. But that's, you can figure those things out, just really understanding nothing more than diffusion equation and a little bit of a law of mass action. So that's kind of fun, and I'll stop there, but thank you.
I've got a question. Have they done this in zero gravity?
In what?
In zero gravity.
In zero gravity.
So, like in space. I was just thinking
in zero gravity,
whether or not the diffusion or the process of the crystals would be different if gravity was removed.
I don't know that they have. Would be interesting. I don't know. Yeah, would be cool. Yeah. Oh, yes.
Can I ask you a question about equations? Because you have when you look at can you go back to your PD system for a second? Just so that I'm thinking about it right. Yeah. So basically, you have the A and B coming together, and the reason you got KAB leaving the second equation, and you just get KAB in the third one is because they join together and count as one. Is that the idea?
That's right.
Yeah. Okay.
That's right. Yeah.
Okay.
Yeah.
And then, and so M is somehow this joined together thing. But what does P stand for here?
Precipitate. Yeah. So A is acid, B is the base, vapor form.
Yeah.
M is the vapor form ammonium chloride. And P is the precipitate solid ammonium chloride. Yeah. So your question's a very good one. I mean, yes, it's true that I wrote M here for monomer, because the way I'm thinking about it is that you have one ammonia, one HCl come together and form this new gas.
Yeah.
Now, there are going to be more steps, a dimer and a trimer and so on, before you really get to the precipitate that you observe. So we could write down a more more complicated set of things in there for sure.
But the last one is the one you see, the P.
That's right.
Okay.
That's right. Yeah, thanks. Yeah, I didn't say much. I skipped over a lot of stuff, but there's whatever. There are boundary conditions and say, that's right. Yeah.
What is counterdiffusion in your title?
No, counterdiffusion, yes, that's what I mean by that is this experiment, because we are diffusing into each other, counter to each other, the ammonia and the HCl. Yeah. So what we should do next is what I call a saturated tube experiment, where we saturate the whole tube with HCl and then allow the ammonia to come in. That's what would be called a saturated tube experiment. And this is where you get fun oscillations again. And there we can do mathematically using that same model to really look at the the oscillations in the front. So we've looked experimentally at the oscillations that occur in a saturated tube experiment and try to get some feel for what's really behind that function f that gives the nucleation. Yeah. Thank you. Yeah.